Oh, this is an extension on the house.
Oh, nice.
You know, see, I get to have all my equipment here.
Nice.
Yeah, it's a good setup. It's a good setup.
All right. I think that we have all of the students here. So, hey, Dave, do you want to intro Lindsay since you know her?
Absolutely. Are we all set? Are we recording? Are we good?
We're recording. We're going. Everything is good.
Awesome. Yeah, so everybody, I'd like to introduce my good friend, Lindsay Miller. She is a remarkable engineer and a really fun person, a very good water skier, and she's going to talk today about her career and the kinds of things that she's been doing since she started work. And actually, your most recent job, Lindsay, I don't even know about, so I cannot wait to hear what it's doing and what the cool stuff you get to do. So without further ado, Lindsay, please take it away.
Cool, thank you. And I'm excited to be here today. And if anyone has questions while I'm presenting, please just jump in. Don't be shy. Most of these slides are just pictures that we can skip through the ones that are less interesting and focus on the ones that people are interested in. So the goal of my talk today is just to show you some of the different things you might work on as an engineer and to really show you the breadth of different things that an engineer can do in their career. And I've had a really exciting time switching between different fields of study and different topics, and hopefully this will just give you an idea of some of the things you might do if you study engineering in school. As an overview, really quickly, my education is in mechanical engineering from Case Western, and that's where I met Dave, and then as well as Berkeley. And then I've interned at Procter & Gamble and NASA, worked at 2 startups, Alphabet Energy and Kelvin, and now I'm at L3Harris as a physicist. And one of the things I wanted to point out with this is that I was a mechanical engineer in all of my education, but my first job was as a process engineer, and then moved into more of a material scientist role for a few years, and then became a director of materials at that startup, which meant I was doing more leadership and strategy and managing a few people in addition to doing some stuff in the lab. And then at Kelvin, where I was last, I was managing a team of 20 data scientists, and that's also just a very different kind of role in a different kind of field. And it's neat that as an engineer, you can kind of transition between these different things. And now I was missing being in the lab and doing science, and so I'm a physicist now and also a program manager, which is where you're more managing a giant project with a big budget instead of managing a big team. So those are some of the overview of what I've done. And through this talk, I'll try to talk a little bit about some of the advice that I've found useful through my career and the 4 points that it kind of boils down to, and I'll revisit these at the very end. But just, I found it really important to be kind of relentless in figuring out what you want to do in an active way. I've never been able to figure out what I want to do just by sitting and thinking about it. I've always found it helpful to read and try new hobbies and try new jobs and just see what you like and see what makes you kind of lose track of time in an exciting way. Another thing I've found incredibly important is once you do know what you want, you need to ask for it, because nobody reads your mind and your boss doesn't know what you want. Your boss doesn't know if you want a promotion, or if maybe you did a really interesting and impactful project and they don't know about it, and you want to be acknowledged for that. You need to ask for what you want. And then trusting your ability to succeed in a new role. I'm kind of going through this again right now as I've started a new job in the last 4 months, and it's in a very different field, but it's really exciting. And so I'm thrilled about it, but you have to keep kind of trusting yourself to take a new role and start in a new field. And I think that's really important. And then finally, as engineers, we sometimes don't like the idea of networking. We think that's like a business person thing. And in reality, networking is just talking and keeping in touch with your coworkers and colleagues and friends and peers. And it's how you end up getting jobs and opportunities. So it's incredibly important to network. Every single job I've had has been because of my network. And that just means someone I knew in grad school or someone I knew who was my boss at my last job, things like that. So I'll touch on those through this. So basically the rest of the slides are just images to show the type of work that I've been involved in. And so I'll go kind of quickly, but please stop me, or at the end you can go back and ask questions. So at an internship, I think maybe somebody is not muted and it's making an echo. Let me try. Let's see. I'm going to mute and unmute real quick. Sometimes that stops the echo. Okay, so when I was an intern at NASA, I was working on in situ resource utilization with lunar soil simulant, which basically means the lunar soil is composed of all kinds of different elements, and including the building blocks for water and rocket fuel. And so if you are going to be staying for a long time on the moon, you might want to be able to make those things or other useful things out of the soil. And it would require being able to uniformly heat the soil to extract the elements you care about. And so I was doing some research into the best ways to mix and heat the lunar soil. So these are some pictures from a paper that was published after I left, but this is some of the stuff I worked on at NASA. There. Then there's a few slides on my PhD research, which was on harvesting energy from vibrations. So the vibration sources were things like motors and fans and HVAC systems, could be washing machines, or any kind of equipment around a building or a house that vibrates, and even transformers and things like that. And so the goal was to have kind of a whole network of wireless sensors that didn't need to be battery powered, or that would have a battery that's rechargeable from harvested energy in its environment. So these are some of the, I did a survey of vibrations, did some simulations and modeling to, and I'll show you the devices here. These are what the devices looked like. They were micro scale devices, so MEMS. I don't know if you're familiar with micro electromechanical systems, but it's sort of the mechanical branch of CMOS chip manufacturing. It uses a lot of the same processes, silicon wafer based. And so I made devices like this that then went inside this package and harvested really small amounts of power from these vibrations in the environment. And the idea, like I said, was to have them power sensor nodes. This was exciting because I got to learn a lot about thin films and all the equipment that's used for CMOS and computer chip manufacturing, as well as sensor and actuator manufacturing. So these are some pictures of the nano lab where I worked, and these are some pictures of the types of equipment that you use if you're depositing thin films or doing some micro machining. I think that's all I've got on that. Are there any questions on those first two before I move on? I'll pause for a minute. I'll tell you a little bit more about what you're seeing here. These are basically a cantilever beam, like a diving board, with a mass on the end that when it's mounted in a package on a vibrating surface, it oscillates, and then a piezoelectric thin film, which is what's here, experiences strain, and piezoelectric materials produce voltage when they're under strain. So that's what these devices are, and then you can wire bond them to a prototype little circuit. It does some power conditioning, and then you can store energy in a battery for charging up the battery to use it for radios or sensors. Any questions? Okay. So then after grad school, someone I knew from my network in grad school had started a company called Alphabet Energy, and they were using thermoelectric materials to convert energy from heat to electricity. And so I went to work there as a process engineer, which means I was working on developing all the recipes and the, kind of the manufacturing processes to create the thermoelectric materials. And quickly it shifted to being a much more research-oriented material science role, where it was actually figuring out how to make the thermoelectric material itself. But this is at a high level, shows what Alphabet Energy was doing, and shows some of the breadth of what you might do as an engineer if you're working in a company. So I'll start with the end product because it's a little easier to picture then. These were the thermoelectric power generators. This large one in a shipping container produced 10 kilowatts, and this smaller one that is on top of a flare stack produced 2.5 kilowatts. And this one was the one that was more commercially successful, and it was basically meant to go on top of one of those oil and gas flares that you see pictures of where there's like fire coming out of the tube. And it was meant to fully combust that natural gas and then generate the 2.5 kilowatts of electrical energy from the wasted gas. So it was a nice efficiency add-on to provide power for these remote sites. And then what was composed of, these large systems were composed of electric modules that were consisted of heat exchangers to allow a cooling liquid and the hot exhaust to go through the system on either side of the thermoelectric package, which is what is pictured here. So the thermoelectric package is then composed of a bunch of pillars of P and N type semiconductor materials, but instead of, so you can think of it almost like solar cells where there's P and N type semiconductors, but the thermoelectric materials, instead of creating electricity from sunlight, it creates electricity from a temperature gradient. And that's what these little blocks are illustrating. And then this is showing on an even more granular level. What I was focused on was really taking raw elements, figuring out the right ways to react those into a thermoelectric material and verify that the material has the right properties, and then generating these ingots from the powder material and eventually polishing them and putting metal on them, testing them for reliability, and ending up with these small elements that go inside the thermoelectric package. And then here are some of the types of machines that are used for that. There's, large ovens and furnaces used to do a lot of the material science reactions. Usually when you're doing material science to create materials from elements, I like to think of it almost like you're doing geology, but at really high speed. So just like geology creates rocks of different kinds by having huge amounts of pressure and temperature and time, we were basically doing the same thing, but in lab scale or manufacturing scale, temperature, time, and combining things in the right proportions to get the reactions that you want. And then here's some pictures of the thermoelectric modules in action here, mounted in the exhaust stream of a car in order to generate electricity for the car. Here's what those modules look like. Here's thermoelectric module on a bench top. So it just shows another thing as an engineer you might do is testing of these things before they're implemented in the final system. So you can see the yellow probes that are there are all thermocouples, and it's just a test bench for that. And then here you can see the big shipping container installed out in the oil field, and this thermoelectric power generator is powering this Santa, which would otherwise be an open flare stack like this, which is very bad for the environment. Any questions on that part before I move on?
I have a question.
Yeah, thought you might.
Are they still in business? Are they still running?
No, it's very sad because we made a successful, like a technically successful product, but from a market point of view, it was very difficult to get past the prototype stage at these oil and gas companies into, and as well as automotive. We were really successful with all the prototypes, but getting those large companies like GM and like, I don't know, all the big oil and gas companies to actually agree to change how they operate and how they manufacture and purchase these things is really difficult. And basically the investors ran out of patience and the company ran out of money. So it's a very interesting experience. Very sad to see like all the technology you work on and get it to succeed, not be able to make it for market reasons, but it's also, it's the way that things work. So maybe one day there'll be a use case that comes up for this technology that's more lucrative, but right now it just, for these companies, they didn't see that it was highly valuable enough to keep purchasing it. So that's just sort of the reality of it.
That's right.
Any other questions? Okay, then after working at Alphabet Energy, another example of network, one of the investors from Alphabet put me in touch with some of his investor friends who have a whole portfolio of different startup companies. And so through that network of investors, they connected me to this other startup called Kelvin that was looking for people. And so I joined Kelvin and started managing their data science team. Kelvin was making software for industrial process control that allowed incorporating data science models into the control loop, and or to just do even simple but custom control logic in the control loop. And so this is a screenshot of what the software interface looked like. And this was really interesting because I'd never worked in software at all. So the data science side is sort of a natural extension of the data work that any scientist or engineer will do. And then additionally, you learn to use the tools and languages like Python and the data science and machine learning packages that exist there. And you learn about a lot of the nuances of how to handle larger data sets. But the software side was completely new for me. And so that was a big challenge. And it was exciting to learn about how software gets made and how it interfaces with the real world. There's not as much to show physically for this company, since what we were making was a software product, but this is a screenshot of that. And it's where I was interested in trying out how I would like being more focused on management and leadership instead of engineering and science. And I really enjoyed it and I learned a lot. And I love the people I worked with, but I started to really miss working in science again. So my boss from Alphabet Energy was at L3Harris and brought me in to interview there. And I didn't expect to want to work in a really big company. I was really enjoying startups, but I was so enthralled by the science they were doing at this facility in San Leandro out here that I was willing to kind of take that chance on trying a big company, even though I liked startups. So what I'm working on now is Pulse Power, which is tell you a little bit about Pulse Power. Is basically the goal is to be able to store up huge amounts of energy in capacitors and then deliver it in a very compressed space and time to a load that is often, the load might be an argon gas or a tantalum foil, something like that. And when you dump huge amounts of energy into that, it generates X-rays or plasma, and that's used for research purposes. So some of that is used for fusion research. For example, imploding plasmas generate basically, it's the beginning of a confined fusion reaction. And that's still pretty research level. And then additionally, there's a lot of reasons that you need to be able to simulate a radiation environment in order to make sure that electronics and optics are able to survive that environment. So that might be for space applications, or it might be for defense. Like if we have an airplane flying over Russia and Russia sets off a bomb, is the airplane going to survive, or will the electronics fail? And those types of questions can be answered using these, they call it a simulator, but it's a giant physical machine. So this one is from Sandia National Lab, because this is public. You can find it on Google. The one that I work on is much smaller than this one, in that it has basically 2 arms instead of 26 or however many this one has. So if you look at these images, each of these sort of like radial spokes that you see is a set of capacitors that's called a Marx bank, and it's basically a set of capacitors that has special switches that are really fast. So you charge the whole thing up. I think this one, let's see. Yeah, this kind of says you charge up for several minutes to reach the voltage that you want. And then the switches are really fast and it discharges into what's called a water line. And it's basically a special circuit that compresses the pulse of energy so that when it finally arrives at the load in the center, which is under vacuum, it's in a nanoseconds, like tens to hundreds of nanosecond pulse. And so it's wild physics. It's really cool. And from this, you can see how big these systems are. So the one I work on is basically just a horizontally opposed pair of these arms. And this system at Sandia is the biggest in the world. This is what it looks like when it fires and it arcs all this electricity. They fill it up with water, DI water as a insulator, So that's why it does that. And here's just an image of the kind of Z-pinch you can get for fusion reaction stuff. So really, I wanted to stop there. I think that's been about 20 minutes. And I know I went through a lot of things really fast, but hopefully I showed you some of the different types of things you could work on as an engineer, and how it's very exciting because you never know what kind of technology you're going to work on next. And there's lots of opportunity to work on both technical and management programs and projects, and both project and program management as well as people management. So that's all I have, and any questions are quite welcome.
Hey, thanks so much. So the students often like to put the questions in the chat. So we'll put them there if you want to go through them. There's one on Root.
Where do I find that? That one, chat. Got it. To be a mechanical engineer, what subjects do you need to be strong in, and what subjects do you need to take in high school, especially AP? That's a great question. I thought that AP Physics and AP Calculus were really valuable, and I'm sure that if you're more interested in the chemical side, AP Chemistry, I'd say really follow your passions. And it's helpful, I think, to have AP classes, but if you don't have them, you can still do very, very well in engineering programs. Generally, you need to enjoy math, physics, chemistry, biology, whatever type of engineering you're going into. You need to enjoy those courses, but I would say even if you're not naturally very gifted at it, if you're willing to work hard at it and you enjoy it, then that's plenty. Like, so I think it's easy to get scared off of some of those things if you feel like you're not naturally a genius at one of those topics, but you should follow your interests and you'll do okay. Difficult to obtain PhD and getting, it was difficult because a lot of it is unscripted, in that in college, you go to class and you get homework assignments and you go do those assignments, and then you study for the test and you get a grade, and it's very scripted in terms of what you need to do. And when you get your PhD, it's not scripted at all. You have to figure out a research topic and figure out what your research questions are and how to ask and answer those research questions, and then how to do those experiments and how to look at the data. And you're usually trying to push a boundary, sort of write papers and do research in an area that no one has done yet, which is why that's how you get your PhD, is kind of push the boundary of science out just a little bit further in one direction, building on what everyone else has already done. And so it's really exciting, and it gives you an opportunity to get very deep into any topic. And so I loved it, even though there were obviously lots of hard days and weeks and months and years, I guess, but I really liked it. And I think in terms of an advantage, I find that it gave me a great experience with that, starting from scratch in a field I knew nothing about and figuring out how to become an expert in that in about 5 years. I find it takes me about 5 years to feel like I'm a world expert in this. I can go present at a conference and talk with anyone about it. That takes me about 5 years. And it's a really interesting opportunity to be able to do that with mentorship from your peers and professors. So, but if you don't get a PhD, you can still have a wonderful science and engineering career. And I know plenty of people who chose to go into industry after their bachelor's or their master's degrees and are brilliant people doing really interesting research work. So it's really what you like, what you want to do. I think all of science and engineering pays pretty well. It's not like, probably if you went into, if what you care about is maximum money, you should probably go into something like, I don't know, law, or I don't know, Dave, what makes a ton of money? Like business, finance people. But you definitely
finance. You want to do 100-hour weeks in New York City? Finance will make you so much
Wall
money.
Street, I don't know. But as an engineer or scientist, you make a really solid salary and you have lots of job opportunities. And so I think it's a really sound financial decision to go into those fields. But I wouldn't go into them for the money. You should go into them because you care about, or you're interested in those topics. The hardest decisions you had to make through my career. That's a really good and tricky question. Well, I would say one of the hardest decisions was when I finished my undergraduate degree, I had a job offer from Procter & Gamble in Cincinnati, and I had to tell them yes or no whether I would take that job before I found out if I was accepted to grad school. So, and I asked them, like, can I just wait a few weeks so that I can find out if I got in or not? And they said, no, we have to know. So I told them no, because it wasn't what I wanted, and I decided I was willing to risk that I'd have to go find a different job. But it felt really hard, or like I had to have, it felt like I had to just go out on a limb to make that decision. And I'm very glad that I did. And of course, got into grad school and it was okay, but that was a hard decision. And I think the decisions about whether to go deeper into management or go deeper into science are hard ones, because, you know, you can always change your mind later, but I think it gets harder. And Dave and I have talked about this. It gets harder as you spend more years away from doing the science to go back to the science. And so those are hard decisions. But yeah, it's a good question.
I just want to jump in real quick and say that we have only 3 minutes left and we have to start the next class. So like 30-second warning, but I'll send you all these questions if we don't get through them.
Okay. Let's see. Well, I'll just go in order, planning out and to obtain the PhD. I think you kind of have to go as you kind of have to be opportunistic, I think, in a way. Like, you have your set of interests, and then you have to see what's available as well. And you kind of learn that any topic is very interesting if you dig in deep enough on it. But I'll try to address that a little more. I'll write out some responses to these. These are all really good questions. And you guys are already active on this first piece of advice of figuring out what you want, because you're doing this program, and you'll find out if this is something you really like.
Yeah, for sure. Thanks so much, Lindsay, for coming to this super interesting topic and very helpful information. So I will send you these questions, and
Great.
I'm sorry that we didn't get through all of them, but thank you so much.
It's great. Thanks everyone. Have a nice summer.
You too. Thank you. Bye.
Thank you.
Thank you.
Thank you.